Ooh, a rate problem with Riemann sums. I love Riemann sums. All right, when we read the problems in calculus, make sure you can identify all the numbers that are in it. And as we read this, we notice a few of these, but I'm going to try to keep this short. So I like to label my pictures too. If they give us pictures, I'm going to label them. As I read on, I started finding some calculus words. I saw the word rate, which is important. I also like to underline the units for the rates, just because that's very important. It's very important that you are identifying which functions are the rate functions. Okay, so let's get down to business. Let's do letter A. When I read letter A, I see a number right here, the number 3, and then I see another calculus concept right here, the midpoint Riemann sum. It's important to identify the calculus concepts when you guys are reading the questions, because sometimes there's other stuff in the question that can distract you from what you already know how to do. If you know how to find the midpoint Riemann sum, don't get distracted by the other things. Okay, so we have an interval goes from 0 to 12, some more numbers there. And since we're doing 3 equal parts, or 3 parts, I just divided it to see what the delta x would be. And then I consider the table that they give us, because what we're doing is we're finding the total amount of water that is pumped into the pool. And earlier we were told that P is the function that is the rate function that tells us the rate at which the water is being pumped into the pool. So we're given those values right there. We're not giving a rule, we're given a table. I don't know if we really need to know that delta x is 4, but it kind of helps in this situation. So let me draw a picture for you guys. All right, so here's our table. Here's the graph. I put all my x values or my t values down at the bottom, and you can see those would be the 3 sections right here. 1, 2, 3. They're the 3 rectangles for our midpoint Riemann sum. These numbers right here, the 2, 6, and the 10, those would actually be the midpoints, which are also given to us in our table up here. And then this is what it would look like if we were to actually graph all those y values of the midpoints and then draw out our rectangles. And so at 2, we see that we go up to 46, and so that's the height of our first rectangle. At 6, which is the middle of our next section, we're going to go all the way up to 57, so that's going to be the height of our second rectangle and then our last rectangle. Honestly, if I was doing this for a test, I probably wouldn't draw this picture. I probably would just draw 3 sections right here on the table to help me see that we go from 0 to 4 and 2 is our midpoint. Then we go from 4 to 8 and 6 is our midpoint. And then that's how I also found my y values. So now we can actually set this up. Okay, so I'm going to write the integral. You don't have to write the integral, but that's what we're essentially doing, is we're trying to find the approximate total amount of water. Ooh, I actually kind of like that. It says amount of water. A total amount. Whenever you're looking for an amount, that usually means that we're finding the antiderivative or the integral. And then I'm going to multiply all the bases times their heights. In this case, all the bases are 4. Be very careful with that. A lot of times when they give you tables, they don't have equal delta x's, and so you're going to have to count those usually. Now, because this is a calculator FRQ, you want to make sure you bring your answer all the way down and simplify it, because they assume that you can use the calculator to do that. If this was a non-calculator problem, a lot of times you just leave the answer right there. You wouldn't have to, like right here. Boom. And that would be sufficient. But since you guys know that this is a calculator one, you need to take it all the way to the end. Okay, let's look at B. Now B is asking us to calculate the total amount. Oh, there's another calculus term. Total amount of water that leaked out of the pool during the time interval. Okay, so we know R is defined earlier up here as the rate at which the water is leaving or leaking out of the pool. Okay, so we have to do the integral of that function. Normally, when you see total, you think absolute value bars. But when you guys look at this function R, you'll see that it's an exponential function, and those never go negative anyways. And so that would be the same as writing it without the absolute values. So in this case, we don't need the absolute values, but it doesn't hurt to write them. So you go ahead and throw that into your graphing calculator, you get your answer. Booyah, done. All right, so far we got 4 points on this FRQ. We got 2 points for letter A, and then we get 2 points for letter B. Okay, for letter C, I found a calculus term right here. It says approximate the volume. Well, actually, that's not quite a calculus term, but that is an amount at times. And then it says, let's see, round your answer to the nearest cubic foot. And it says use A and B. Okay, so we have to combine A and B. Now remember, A is the amount of water that's being added to the pool, and B gives us the amount of water that has left the pool. And then don't forget the very beginning, the initial condition, we were told that the pool already has 1,000 feet or cubic feet in it from the beginning. So we got our 1,000, we're going to add the 660, and then we're going to take away the 225. Using our calculator, we get this answer, and because they said round your answer to the nearest cubic foot, I can write out 1,434. Now, I don't have to write the units, but I'm going to anyways. And the reason why I don't have to is because they say it in the problem right here in the question, which means they're not going to be giving me points for those units. But the answer is 1,434. Okay, now letter D, our last one. It says find the rate, which is a calculus term. Find the rate at which the volume of the water of the pool is increasing at time t equals 8 hours. And then it asks a question, how fast is the water level in the pool rising at t equals 8? So we got 2 questions here. In the end, it also says indicate units of measure. I want to make sure I do that because I didn't have to do that earlier, but here they're telling me to do it, so I will make sure I do that. The first thing it says to do is to find the rate at which the volume of the water in the pool is increasing. Okay, so that's a new rate. We have the rate of water entering. We have the rate of water leaving. Now it wants to know the rate at which the volume is changing. And so I'm going to define that as dV/dt. And to find that rate, I'm going to have to take the rate at which the water is entering the pool and subtract from that the rate at which the water is leaving the pool. There, we put our negative right there. Okay, so dV/dt at 8. And so I'm going to plug 8 into each of these guys. Oh, it looks like I forgot my negative again, so I'll put my negative right here. And then I'm going to plug 8 into the P and plug 8 into the R to see what we get. Oh, look, when we plug 8 into the P, we get 60. And then when we plug 8 into the R, we get, well, this nasty thing right here. And let's not forget our negative. Now remember, this is a calculator FRQ, so that means we're going to have to plug this in and simplify it down all the way. So after plugging it into the calculator, I got 43.242, and it's cube feet per hour. I think that's huge right there. We need to make sure that the feet is cubed because this is volume, and it's per hour because we are dealing with a rate. Okay, so that's the first part of the question. The second part of the question asks, how fast is the water level in the pool rising? Water level would be the same as H, and they define for us the volume of this cylinder right here with the H. So it looks like we're trying to find dH/dt. So to get dH/dt, we're going to have to take the derivative of the volume function with respect to t. And before we do this, we can simplify it a little bit more because R doesn't change in this scenario. The radius stays the same no matter how high or how low the water level is. And so because R doesn't change, we can go ahead and plug in what R is at 8 hours. And R is always going to be 12, so I'm going to cross out R squared and put 144. And now take the derivative. This is going to be a lot better now that I don't have to do the product rule. So I take the derivative, I get dV/dt equals 144 pi times dH/dt. That's because the derivative of h with respect to t is 1, but then you have to multiply that by dH/dt. Okay, and then I'm going to plug in dV/dt from what I got earlier. And then that and then I'm going to get the dHdt alone by dividing both sides by 144 pi. And then we can't leave our answer like this. We have to simplify it all the way because this is a calculator problem. After plugging it into my calculator, I get 0.096, and then notice my units are feet per hour. That's because the height is a linear measure. It is not an area and it is not a volume, so we need to have it as feet per hour.